I mentioned in the beginning, on the beginning of uh, I mentioned in the beginning of lecture 8 that the derivative, one of the questions that mathematicians in Europe had when they first developed calculus was this notion of velocity. And it turns out that the derivative can be used to determine the slope, and as such, it can also be used to determine the rate of change of one variable with respect to another variable. And these applications of the derivative often involve the rates of change that occur in a bunch of fields like physics and chemistry, and even aerospace as well. Like if you ever wonder um, how how NASA, for example, when they send a rocket to space, the International Space Station, how they calculate the trajectory, the speed that the rocket must be going. Well, they use a lot of calculus throughout. They use very difficult functions, but uh, within those functions, they also apply various calculus techniques. And first and foremost, they definitely utilize the derivative. Um, Now, a common use of the rate of change is often to describe the motion of an object as it moves on a, let's say, on a straight line, or on a function like on a slope. So if you have something like this, like an object is falling, then you could use calculus to determine the speed and the velocity at which the object is actually falling. So, um, so oftentimes these functions, or these position functions, give you um, the position of an object with respect to the origin of an object with respect to the origin for some time t. Okay. Often these functions are given in the form of s of t. So whenever you see s of t as a function, like s of t equals 2x squared plus 5, then this is referring to a position function. Specifically how the position is changing with respect of time. You may remember for linear distances that the rate of change is rate equals distance over time. Distance divided by time. So like if you were traveling, I don't know if you remember these problems, like you're traveling a certain distance at a certain speed. How long does it take you? Or you travel this distance at this rate. You know, you could manipulate this to get different formulas. Like if you wanted to find time, then time times the rate that you go is equal to your distance traveled. So if you want to find the distance, simply you multiply the time by the rate. Um, Similarly, you could find the time you spent by dividing the distance over your rate of speed. So you could take time, and time is going to be equal to the distance traveled divided by the rate at which you travel. So for example, if you're traveling 60 miles at 20 miles an hour, then you know it's going to take you 2 hours to arrive. Okay. So these are very useful, and you use them all the time. I mean, you don't even realize it when you use them, but you do use them all the time. But anyway, let's talk a little bit about an actual example, so you can see what I'm talking about. These are the so-called rates of change problems. So they are very common in a calculus class. Wherever you go in a standard calculus class, you will see them. Later on, we will also see something called related rates. Once we learn more of the rules of derivatives, which will be somewhat related to this velocity and acceleration problems. So this is one example. Maybe we'll do two. So if a billiard ball is dropped from a height of 100 feet, its height s at time t is given by the function position function s of t equals negative 16t squared plus 100 plus 100, where s is measuring feet and t is measuring seconds. Okay, so the question is to find the average velocity over some time intervals. And the first time interval that I'll do will be 1, 2. Okay. So if you remember from before, we had whatchamacallit, we had a formula for this earlier in the semester, and we even saw it earlier in section number 2. So what's going to happen is we're going to have the change in y basically over the change in x. That's basically what this boils down to. This is going to be, let me write it down, this is going to be delta s over delta t. Remember, delta s is just going to be that change in y, delta t is going to be the change in x, because we get a choice on what the t value is. So if we're looking at this interval of time, we're interested in seeing how much the distance changed between traveling from 1 and 2. Well, how do I get the s's, the delta s's? Well, that I get by evaluating the function at the endpoints at 1 and at 2. So s of 1, the object is falling from this height at s of 1, and that height is going to be given by negative 16 times 1 squared plus 100. So that's going to be equal to negative 16 plus 100. Last time I checked, 100 minus 16 I believe is 84. And then for the second one, if we now take the right endpoint and evaluate the position at 2, then we have negative 16 at 2 seconds. So this is in terms of seconds, because remember t is in seconds. After 2 seconds, the position of the object of the ball is negative 16 times 2 squared plus 100, and 2 squared is 4, minus 16 times 4 I believe is 64, so it's really minus 64 plus 100. So 100 minus 64 should be 36. Yeah, 36. And now we can actually figure out what the average speed is, the slope. There's going to be 36. Well, I get to pick whichever I want, so I'm going to pick the 36 first. So 36 minus 84 divided by 2 minus 1. So 36 minus 84 is going to be equal to negative 48, and 2 minus 1 is 2, so it's 1. So we got negative 48 feet per sec. So we have that the ball is falling at an average velocity of negative 48 feet a second. You could do this for another interval. I'm going to leave this one as an exercise for you to try it. Do 1 and 1.5. It's a very simple process. All of these natural velocities will be negative, so this is something that you should see. This is a negative velocity. Velocity, which means the object is falling, and it should be. It's falling. Why should it be falling? Because we said that we were throwing the object down from a height of 100 feet. The ball is being dropped from that particular height. Now this is the average velocity. This is how we find the average velocity. Um, that's what I meant to say earlier when I said that we covered this already. So this is the average velocity. I believe this was the first example that we did on limits. When we first began talking about limits, we began talking about this average velocity problem. Now, what we could actually find is the so-called instantaneous velocity. And this is what the derivative helps us locate. Okay. Now, for the instantaneous velocity of a particular object, you can approximate the slope of the tangent line by simply approximating the slope of the secant lines. Now, it turns out that we can use the derivative of s of t to actually find a so-called velocity function. We can use, so let me write that down, we can use s prime of t to find a velocity function, whereas s of t, so s of t was a position function, s prime of t, its derivative, is a velocity function. And oftentimes, instead of writing s prime of t, you may see this as just v of t. Okay, so v of t, the velocity function of t, is simply the limit as t goes to 0 of s of t plus delta t minus s of t divided by delta t, which is again the definition of the derivative of s of t. So this is actually extremely useful when we're dealing with problems like this, with position and velocity. For example, let's do one more example to illustrate this. So at a time t equals 0, a diver jumps from a platform that is 32 feet above the water. The position function of the diver is s of t equals negative 16t squared plus 16t plus 32. So that's the position function, and here s is measuring feet, and t is measuring seconds. And we have two questions. Number one, when does the diver hit the water? And number two, what is the average velocity at impact? Velocity at impact. Well, we have a function for position, right? We know when the diver is going to hit the water. When does the diver hit the water? When his position is 0, because he's up 32 feet in the air. So if you can't visualize this, sometimes it's useful to draw it. So let me actually draw it for you. So let's say you have, I'm pretty bad at drawing things. So let's say this is stairs, pretty dangerous stairs at that. And let's say you have the diving board. In my mind, the diver was up here. Let's say you have the pool down here. So he's going to jump down into the water, and the distance from the diving board to the water is 32 feet. That's what we're saying. Okay, so this is why in the function given above, in s of t, which is giving us negative 16t squared plus 16t plus 32, this is where we have the plus 32. Because if you were looking at this on the Cartesian plane, then this is a parabola that's concave down, whatever that word means it's frowning, going down like this. But this y-intercept right here is 32. And then down here, whatever point that is, that's where you hit the water. The x-axis here represents the water level. So if we could find out what the zero of this function is on that side, then we're good to go. Well, how do we find out the zero of this function? Well, we set it equal to 0 and then we solve. Or we use the quadratic formula. This one is not terribly difficult to actually solve by factoring, so we're going to do it. So first things first, let's set this equal to 0. So this is negative 16t squared plus 16t plus 32. When is that equal to 0? That's the question. Remember, this we do to find the zeros of the function, where the function hits the x-axis. And we're going to get two values because it's a parabola. Well, notice that everything here is a factor of 16. So we could pull out a 16 from the inside. In fact, I could pull out a negative 16 and just keep everything in the inside to work with positive values. So it's going to be t squared minus t minus 2. Minus 2 equal to 0. Now we could factor the inside. The reason why we could factor the inside is because we have negative 2 times 1 gives you negative 2, but they add up to negative 1 t, so we can factor that. So we have t plus 1 times t minus 2 equal to 0. You could verify this. And now there's a rule that says that if you have a times b equal to 0, then either a equals 0 or b equals 0. So that means that either t plus 1 equals 0 or t minus 2 equals 0. So what values make this be 0? Well, t equals negative 1 makes this one 0, and t equals 2 make this one 0. 16 is just 16, so we don't have to worry about it. So we have t equals negative 1 or 2. But which one is the actual solution? Well, time is positive. Time is not negative. We're not going back in time. So since t is positive, is bigger than or equal to 0, we choose the positive solution. This is always going to be the case. And you could see that from the graph above. You know, when I drew this, I said that the diver is jumping on this direction, not backwards. Okay? So we choose a positive direction, which means that the diver hits the water at 2 seconds. So the diver hits the water at 2 seconds, at t equals 2 seconds. Finally, the second part of the question was to find the velocity at impact. Now this is a more difficult question than the one where we had to find the average velocity. See, the average velocity, we were just looking at 2 points on that graph and taking the average. Here we want to find the exact velocity that the diver must have had at impact. And to find this, we have to take the derivative. So the velocity at time t is given by the derivative. And when I say the velocity, I mean the instantaneous velocity is given by the derivative s prime of t And what is the derivative of s prime of t? Well, s of t is equal to negative 16t squared plus 16t plus 32. So s prime of t, well, the derivative of this piece is 2 times 16, so it's negative 32t, and then plus 16t. The derivative of 32 is 0. So plus 0. You don't have to write it. Not 16t, plus 16. The derivative of 16t is just 16. Remember, you take the 2, bring it down, multiply by the 16, and then you minus 1. So that's where we get negative 32t. Now, we have to simply evaluate the derivative at 2, because that's the time at which we impacted the water, and we want to find the velocity at impact of the diver. So now we plug in t equals 2 into the derivative. So into derivative. So what do we get? We get s prime valued at 2 is equal to negative 32 times 2 plus 16. Well, negative 32 times 2, that's negative 64, plus 16, that's equal to negative 48 feet per second. And this is how you go about solving this type of problems that involve instantaneous velocity. So, again, we say the instantaneous velocity at impact of the diver was negative 48 feet per second. Okay. Thank you for your time.